what I'm going to talk to you today real quick about is sort of the research efforts that we're undergoing up in Rome, upstate New York. And in particular, we are working on IBM's 20-qubit Poughkeepsie chip. And we're just coming up with some experiments to sort of get a feel for ourselves and to also sort of get some insight into algorithm design. That's our primary motivation. So there'll be three main parts to this talk. The first part is we wanted to verify for ourselves sort of the qubit qualities. There's lots of forms of qubits, and there's lots of mathematical descriptions of qubits, so we wanted to go in for ourselves and sort of verify those. Then next, in sort of the pursuit of not perfecting algorithms or just trying to find the optimal result of algorithms, we're more motivated by, okay, so if you try this and this and this, what insights can this help us to sort of lead to bigger algorithms? And to do that, we implemented some 3-qubit algorithms for the Toffoli gate, or the CC naught, and the QFT, which are just small circuits. And we implemented them in different ways on different qubit combinations. And so you'll see some actual generated experimental results from the Poughkeepsie device. All right. So kicking things off, here's Poughkeepsie. It is a 20-qubit chip. What you see here are the colors and the lines indicating your connectivity, which is a big issue in this talk. And then the colors sort of are the noisiness of these qubits. So the first model of noise that I'm going to talk about is sort of decoherence. And this is a big one. This is one that plagues all NISQ devices currently. And it's sort of a probabilistic decay. And the problem is when you put a qubit in a one state, you want it to stay there. And so if it has a spontaneous chance of decay, that can seriously cause problems in an algorithm. So our approach to verifying this on the IBM chip was to just design a simple experiment, and we wanted to just literally see decay happen. That was our goal. So at the top here, you can see the formula, probability as a function of time. It's an exponential decay. And then to test it, the circuit was quite simple. It's right there. You start with a qubit in the 0 state. You excite it up to the 1 state using a X gate, which has a high fidelity. And then you just wait. And then you make a measurement. Now, to wait on this device, you can just use identity gates, which do nothing. So you're confident that you're not introducing some other form of noise. You're literally just letting the qubit be itself. OK. So here's the first sets of data I'm going to show you guys. So here's 4 batches of data that I picked out. Up in the top right, those are the T1 times reported by IBM. And then here is the data. So as you can see on the x-axis, we have time in microseconds. And then on the y-axis, this is the probability of the qubit remaining in the excited state. And certainly, these plots look exponential. But of course, we had to go in and verify for ourselves. So here are those same 4 plots now fit to an exponential curve. And on the right-hand side, you can sort of see this is what IBM reports on whatever particular morning that they did their checks. And then on the right was what our fits. And in my opinion, they're pretty close. But more importantly, that they show that the qubit is behaving exponentially, which is more important because that means your qubit is doing what it's mathematically supposed to, and then that's how you can factor it into your algorithm design. So that was T1, which is sort of the simpler of the 2 noise models. Now, the more complicated of the 2 is right here, T2. I had to remove it from my slides because it's a little bit more technical than needed. But again, we wanted to go in ourselves and see, OK, how are these qubits behaving? Now, this particular set of data came from a Hahn-Echo experiment, for those of you who know what that is. For those of you who are interested, I can field some questions later. But once again, this is another form of noise that you have to consider when you're working with these qubits. And this one has to deal with superposition, so it's particularly more important because, as we know, superposition is what allows these algorithms to produce speedups. So what you're looking at here is essentially the rate at which a qubit is losing the ability to hold its superposition. Now, it's a little bit more technical than that. It's not as simple as just a decay. But it was really nice to sort of see, okay, these are the reported IBM times. We do the Hahn-Echo experiment, and the data seems to match. Now, to be fair, those plots I just showed you were quite nice. Not all data comes in that form. And so for those of you who are interested in getting on these devices and maybe lack sort of that kinetic feel of, okay, what does it feel like to put on a circuit and to play with real qubits, sometimes they're noisy. And sometimes you have to just sort of throw away some data because it didn't come out quite right. Here, these are just 2 random data batches I grabbed. And so this is sort of, illustrating that we are not the only people on Poughkeepsie at the Air Force. There's lots of people. And as you can see in some of these plots, it looks like halfway through the experiment, the qubit just went and did something else. And that's perfectly understandable, because in the middle of a work week, we're not the only ones on it. We have to share this device. So just wanted to put that out there, that it's not always about just getting the best results. Sometimes you have to appreciate, okay, where are these qubits, and how do I how do I deal with real noise? And sometimes the answer is just throw it out and do it over. Okay, so the next thing is gate fidelity. And gate fidelity is a big issue, single and double gates. And in particular, our approach was we wanted to see how good C naughts were. Because C naughts are sort of the real workhorse of most algorithms. And when it comes to algorithm design, you've got this chip, but they're not all interconnected. So C naughts are the sort of first approach to supplementing lacking connectivity. As you see here, I just picked 2 qubits, C, T for control and target. And you already have choices. So if you want to go and put your algorithm on a real device, you have immediate choices of, okay, where do I put my connections? What qubits are better than other qubits? So that's what we're interested in. Now, in doing this C naught chain experiment, as we sort of call it, I just wanted to sort of show you that it introduces new consequences. When you read an algorithm like Shor's, Bernstein-Vazirani, Simon's, Grover's, those are all originally designed so that all the qubits can talk to all the other qubits, and it's a nice theoretical. But now when you have to supplement that with C naught chains, you have to introduce Silla qubits, which have been brought up before. And the question comes down to what do I require of my Silla qubits? Do I need them one time, in which case they're disposable in essence? Or do I need to use them multiple times throughout an experiment, which is more likely? So in the latter case, when you need to recycle Silla qubits because you need to run them through multiple C naught chains, now you have choices. And that's sort of what you can see down here in the bottom plot. The top plot is just a basic C naught chain. You've got qubit A that wants to do a C naught on qubit B, but qubits 1 and 2 are in the way, so what do? Well, you just string along a bunch of C naughts, and that's that. But now at the bottom, that same circuit, essentially, these are the ones we tested, and you'll see the results coming up soon. On the left, that is sort of the basic approach. You just excite the first qubit, and then you run a chain of C naughts. In the middle one, you secondarily put X gates on your Silla qubits to bring them back down to the 0 state, essentially resetting them for the next person who wants to use them in the algorithm. And you can see at the bottom of each circuit what the predicted final state is, and you can see that there's zeros. And then finally, the third one on the right uses more C naughts to essentially undo it. Now, why would you do that? Because that is way more costly in your algorithm. And the answer is superposition. If the algorithm or qubit A has a superposition, you can't just simply use X gates on your Sillas anymore. And so you have to essentially protect against that with more C naughts. And you'll see these results right here. So the first result, first I have to explain to you the sort of criteria. So when doing these experiments within Sillas, we sort of define 2 metrics. The first metric is a success metric, which just means, did my control qubit and my target qubit both end up in the 1 state? Because that was the ultimate goal of this chain. And then on the bottom, what we call the perfect success rate, that incorporates the Silla. So not only did my control and target end up in the 1 state, but were all of my Silla qubits also exactly where I predicted them to be. And so we did this on the Poughkeepsie device, and plotted on the x-axis is the length of the chain, from 1 to 2 qubits all the way to the maximum. So all 20 qubits get touched and put into the chain. And from this, we learned a couple interesting things. So one, the use of X gates to reset the qubits didn't impact the success rate. So those are the 2 top green plots, and that's really good. Theoretically, that makes sense because those X gates are coming after the C naughts, so they shouldn't really affect it. But then when you use C naughts, you've now doubled the length of your circuit. And if you've doubled the length of your circuit, you've doubled the opportunity for T1 errors, so the lower success rate was expected. The perfect at the bottom, that was quite interesting because you can see there's quite a large gap between using X gates to reset your qubits, you're in Silla qubits, versus doing nothing versus using more CX gates. And then we asked ourselves, okay, why would this be? And it comes back to, again, the T1. If you have 20 qubits and you excite them all, you go back to the formula for probabilistically, okay, what's the chance that one of those 20 qubits is going to spontaneously decay? And that's sort of what you're seeing at the tail end of this graph. It's just very, very hard to expect all 20 qubits to hold their excited state. So conversely, if you don't expect that, you use X gates to put them back into the 0 state, you can get away with much higher success rates. And we thought this was quite cool. Okay, so building on that, so now I just showed you sort of a rough flavor of what it's like supplementing connectivity. And we wanted to just try some algorithms. In particular, we went for the simplest case. We decided, let's do some things with 3 computational qubits, particularly just because that connectivity doesn't exist on Poughkeepsie. It does on Tokyo and others, but working on Poughkeepsie, we thought this is a good opportunity to sort of see what is the real impact when you don't have the connectivity you want. So what did we do? Well, we pursued the same algorithms using 3 computational qubits, but we tried to implement it in different ways and see who was the winner, more or less. So what you're going to see is a bunch of different qubit combinations using various amounts of ancillas. I can jump to the first one here. So straight off the bat, if it's a 3-qubit algorithm, let's just use 3 qubits. And we'll put them all in a line. And there's plenty of these on Poughkeepsie. There's a total, I think, of 32 combinations. We tested them all. We weren't really interested in who's the best, because that changes day to day, week to week, month to month, right? And as qubits get better, gates get better, it's sort of an empty stat to say, like, on this particular day, these 3 qubits were the best. But what's more interesting is sort of the technique and how that changes as you move through the circuit. So what you're looking at here is how to implement a control from qubit 1 to qubit 3. And like I mentioned earlier, the issue is now having to deal with superpositions, but here in particular, qubit 2 is not an ancilla. It's a computational qubit. You can't just string C naughts through it, hit it with X gates, and leave it alone. It holds a part of your algorithm. It's important. So you have to protect it. And what I've drawn here is I've sort of just diagrammically drawn the same thing in 2 forms. These 3 C naughts that bounce back and forth, that's a swap gate. And swap gates are more or less your answer when you have qubits that you need to protect their quantum state. So there's ways to make this more optimal. For instance, you could drop that last swap gate, save yourself 3 C naughts, which is a big deal. And then your final measurement, you just interpret the results between qubits 2 and 3. So there are lots of optimization tricks to be played. But the results that you're going to see are sort of purposefully bad, I could say, in a way. They're not bad, they're just like the standard approaches. Because maybe on one case, you can get away with swapping qubits 2 and 3, and you don't care who measures who. But now if you have 15 to 10 to 20 qubits, and it's just a small part of a larger algorithm, you need qubit 2 and qubit 3 to stay where they are. So that's sort of the motivation for maybe being the less optimal. All right. Second pattern is let's just bump up the number of qubits, and let's add 1 ancilla. So what does this do? Now we don't have to traverse through a computational qubit, and that's great, because traversing through computational qubits using swap gates, as I just mentioned, is problematic. So instead, we put one in Silla, and we force all of the connections through that one in Silla. And here at the bottom, you can see, once again, the two techniques, depending on whether or not I have superposition. If I don't have superposition, I can get away with just an X gate to reset the central in Silla. And in the harder case, if I do, well, then I'm forced to use more C-naughts, which is not so problematic. And then lastly, based on those two, which we predicted, we were curious to see which would perform better. So that was the motivation for this. Does the addition of that one in Silla boost my success rates of my algorithm or hinder it? And then just, because we have the device and we've got all these qubits, we decided, okay, let's go for 6. And the two geometries you're looking at here were picked because they share that same feature with the two that I just mentioned. The top geometry, where the in Silla qubits are sitting in between my 3 computationals, that shares the same principle as the 4-qubit. Because each computational qubit talks to another computational qubit through exactly one in Silla. So the results of the 4-qubit we expected to match with that. Similarly, on the bottom half, the 3-qubit geometry is sitting right there in a line, qubits 1, 2, and 3. And then the question is, okay, if I have the option of traversing through the central qubit versus a C-naught chain around the ring, which is going to win? Am I going to get a higher success rate by introducing these 3 in Sillas? And that's what we wanted to find out. So now the question is, okay, what algorithm and how do we benchmark these? There's lots of great algorithms, and we just happened to sort of do a little bit of common denominator across them, and we came across the C-naught and the QFT as being pretty two influential subroutines. So those are what we're going to show you the results for. So getting started, the CC naught, also known as the Toffoli gate, it is the sort of upgraded version of just a regular C naught. Now you've got 2 control qubits, and you have 1 target. So the same rules apply. You only bit flip the 3rd qubit when the first 2 are in the excited 1 state. And so here you see the sort of standard Toffoli gate circuit. And I call it a gate, but it is really a circuit. When future technologies come out, who knows? It'll just be a gate in itself, maybe. And here's the stats for it. So a total of 6 C naughts, 9 single qubit gates. So the fidelity at the end of the day, that's what we're benchmarking. And because we don't have superposition, the results you're going to see use X gates to sort of reset in Silla qubits where needed. And then again, here's the reminder of sort of blindly throwing in these tactics. So again, there are optimal ways to do all of these. And if we sat down and wanted to, we could boost all the success rates you're about to see by using clever tricks with C naughts and measurements. But that doesn't tell you how things scale. That just tells you how good it was on that particular qubit, on that particular day. And we were just more interested for the long haul. So how do these techniques scale? And so you've seen the 2 circuits on the left and middle, and then on the right, that's sort of the 6 qubit in Silla, just showing you, if you can imagine taking one of those C naughts in the upper circuit and replacing it now with this long circuit on the bottom right, that shows you sort of the real cost of what it means to work on a NISQ device. You have to just blindly hit it with so many more gates than you originally theoretically needed. Okay. So here's some preliminary results, and we're still generating some as this talk is even going on, I'm sure. The 3 and 4 qubit, which we were the contenders for who was better, we found that the 3 qubit had the slight edge. And again, these high, lows, and averages, these were averaged over many experiments, over many days, over many qubit combinations. We tried literally every combination. Every qubit got a chance to be both a computational and in Silla. And this is sort of the average results. And they're great. They're showing you the success rates, but they're not so insightful into algorithm design. They just show you how good it is currently. Jumping to the 6 qubits, this is where we actually saw something interesting. So I mentioned that these 2 qubit designs were sort of introduced to mimic the 3 and 4 qubits and sort of copy their problems, if you will, and put them on a larger. And what you'll notice immediately is that on the left circuit, those success rates, which is, again, did the control and the target qubits both get in the one state like I designed, took a major hit on the left, as you can see. And that's really interesting, because we asked ourselves, what's different? We have 3 computational qubits, that's the same, and each connection that needs to be supplemented just goes through one in Silla. That's the exact same as the 4 qubit. And so we're actually still currently testing why it was so bad, but we sort of have a hunch that just carrying around the extra in Silla qubits really sort of, it made it a lot more challenging for the in Silla qubits to hold on to their excited states. And since it's not the same qubit each time, we went back and checked, and sure enough, when one qubit drops, and then you have to wait for the next qubit's turn, and so that's still an open question, I'll say. But the right-hand side was sort of nice because it showed that you can supplement that outer connection, and you still get pretty good success rates. Okay. The second one, QFT. QFT is another workhorse of quantum algorithms, and it always seems to come like right at the end of an algorithm. It's sort of like the secret sauce, if you will. You do all these amazing things, and then like magic, the QFT just pops out the answer. But when benchmarking it, it doesn't have a sort of concrete final state like a Toffoli gate does. If you run that circuit and you work it out mathematically, what you get is a superposition. And you can't really benchmark a superposition because when you go in and probe it, especially this one because they're all equally probable, you don't really know if it was doing its job. Because the role of the QFT is phase, and that's where its power comes from. So anyway, here's the circuit. And in the middle one, that is a control rotation gate and how you implement it. Standard approach. Sure, there's more optimal techniques. So what we thought was interesting is, okay, let's try to come up with an algorithm so that we can benchmark the QFT. We want a single final number, a percentage. And we decided to pick phase estimation as our base model. So phase estimation is a very promising algorithm. It essentially has the promise of being able to detect an eigenvalue of some matrix U. And so what you're seeing here on the right-hand side is the standard QPE on top, and then our experiment on the bottom. Now, there's a lot of challenges when it comes to implementing an actual phase estimation. Number one is, what does it mean to do an arbitrary control U? That is an unanswered question. What does it mean to just put in a random state, or no, excuse me, an eigenstate of any choosing? Sort of, I would say it's not easy to prepare quantum states, and it's even tougher when those quantum states have to be specifically eigenstates of U's. And so you work through the math, and then you realize, okay, well, all this algorithm is really doing is absorbing phases in powers of 2. So you can get away with essentially mimicking the phase estimation by just using single qubit control rotation gates. That's the R of phi, 2 phi, and 4 phi there you see at the bottom. And that's pretty nice because when now we go to benchmark our QFT, the only extra noise we added was these single qubit gates, which have really good fidelity, so we know that that isn't going to kill our results. Okay. So we're still working this out, but here's what we found. And it was quite interesting, and it was not what we expected. Here again, we see the success metric and the perfect metric for when you have in Silla or not. And what immediately jumps out at you is that the phase absolutely plays a role here. It's not a consistent benchmark. It depends on what phase you're using. And not only that, there seems to be some sort of pattern that's repeating every quarter cycle here. So some phases are easier to detect than others. Why is that? Well, that's what we wanted to know. And we're still working on it. It's still an open question. But we have a hunch that it has to do with the complexity of the state. So when you go back and you look at QFT and you sort of see, okay, well, what are my states? What amplitudes are they holding on to? What phases? You notice that, okay, where the success rates take huge hits, those correspond to states that have the maximal amount of sort of diversity in your quantum state. With the 3 computational qubits, you have sort of 8 different states. And when each of those 8 states has a unique phase totally different from the other 7, that seems to correspond with where the dips are. And I can't go into full details on this, but I'm happy to answer more technical questions because this experiment, I think, was particularly insightful. Because if you're now designing an algorithm with QFT in mind, if this is a consequence of NISQ, where certain phases are easier to detect than others, that could drastically change or give you an advantage when designing your algorithm, your use case, what have you. So that was what we were after. Again, on a given day, on a given week, 1 qubit could be the best qubit, and that's not what we were after. We were more after things like this, insights that will help us scale in our algorithm designs as we go into the future. So, quick summary of what we did. We experimented, we verified T1 and T2 times, which currently are in the range of 50 to 100 microseconds, improving all the time. We essentially tested C0 fidelity, but we did it in an interesting way using chains, because that seems to be sort of, for at least maybe a year or two more, looking at future designs like the next generation of IBM with the 53 qubits, C0 chains might be very, very crucial, just based on the geometry. And then lastly, we started to throw these things at what we consider 2 of the most core subroutines going forward, the Toffoli gate, the CC0, and the QFT. We know that there's no way we're going to reach quantum advantage without these 2 powerful workhorses. So we figured, why not? Let's just test them. But test them in a way that we don't just get sort of a trophy at the end of the day for who was the best, but we get insight into using different qubit geometries and what have you. So with that, I think I have about 2 minutes of questions. Thank you all for listening. She's coming.
Thank you. Yeah, so real simple question. So this seems almost like a genetic footprint of this particular machine that can be used to fine-tune our algorithms when we run on there. Mm-hmm. Does that imply that every machine's going to have a different set of tuning parameters, if you will, or strengths and weaknesses that will have to be considered for algorithms?
I would say, yeah. When you're looking at your algorithm and you're trying to figure out maybe who is the best format for it, these are the things that you want to look for. Who has the right connectivity? Who has the particular T1, T2 times that I'm interested in? And then when you move to a different chip, that all changes. And when you move to a different qubit technology, that all changes. For instance, we've already heard throughout this conference that ions have an advantage when it comes to connectivity, so that you maybe have much higher success rates from distance qubits talking to each other. But is there a trade-off somewhere else? In phase detection and whatnot, perhaps. So yeah, it is. All the results you saw are Poughkeepsie. They're not just general results. They are very specific to just Poughkeepsie, in particular Poughkeepsie from November to December, because it will always be changing. One back here.
Hi, that was a very nice talk. Thank you. So, question about your T1 and T2 benchmarking experiments. Mm-hmm. Did you code up those circuits yourself, or were you using other parts of the Qiskit stack, Ignis in particular, to do that?
So all the results you saw are hand-coded by us. We work with Qiskit. We send the circuits to IBM. First, we play with them on the simulator so that we know what the final answer is going to be theoretically. But no, we just have Jupyter notebooks, and we send them off to IBM, and then they just send us back numbers.
Thank you.
So we're a good representation of what an average user would be in that sense.